Welcome dear students. In this video we will discuss equilibrium of rigid bodies. Now for a rigid body in static equilibrium, all the external forces and moments should be balanced. That means that there should be no translatory motion as well as no rotatory motion. So as in the case of particles, when we studied the equilibrium of particles, then we see that there is no unbalanced force and all the resultant forces should be zero. Similarly, for a rigid body to be in equilibrium, the necessary and sufficient condition is that all the forces and moments should be zero. The resultant of all the forces and resultant of all the moments should be zero. That means summation of all the external forces should be zero, and similarly summation of all the moments at a particular point should be zero. And this thing we can also write in the form of rectangular components. So we will be having six scalar equations. So for forces, summation of fx should be zero, summation of fy should be zero, summation of fz should be zero. Similarly for moments, summation of mx, summation of my, and summation of mz should be zero. Now first step to solve the rigid body equilibrium problems is to prepare a free body diagram. Okay, so suppose this is the figure, this is our rigid body. Okay, so first step is to prepare a free body diagram. Okay, so this is the actual figure, and now what we have to do, we have to select the extent of the free body and detach it from the ground and all other bodies. Okay, so here we have prepared a free body diagram and we have detached the bodies from here. So because our body is connected here, but we have detached it, and now we have to indicate the point of application, magnitude and direction of external forces including the rigid body weight. So we have to show all the forces. Okay, so for example, here a weight is hanging, so we have to show this force. Then we have some weight of the body, so that can be applied at the center of gravity. So this is shown here, and then we have some reaction forces. So this is a roller type of support, so here we have this reaction, and here we have this type of reaction. Okay, so we have to indicate the point of application and assume direction of unknown applied forces. If we do not know the direction of any force, then we have to assume some direction, and then we have to show the direction of unknown applied forces. These usually consist of reactions through which the ground and other bodies oppose the possible motion of the rigid body. So you have to identify the reaction forces, means from where the reaction forces might act, and you have to assume some direction for that, and then you have to show on the free body diagram. Then include the dimensions necessary to compute the moments. So because whenever we are calculating the equilibrium problem, then we need to calculate the moment and equate it to zero. So we need dimensions. For example, in this case, we have these dimensions 2 meter and 4 meter and this 1.5 meter. So these dimensions should also be included in the free body diagram. Now let us understand the reaction forces when there is some support, because whenever you are studying the equilibrium problems for rigid bodies, then you will have to show the unknown reactions. So how you will be showing up those reactions? So let us see that. Now suppose your body is having some roller type of support, this type of support, or some rocker type of support, or your body is placed on some frictionless surface, then you will be showing the reaction as normal to the surface. Okay, so the reaction will always be normal like this, means perpendicular at the point of contact. So the direction is known line of action, that is always perpendicular. Okay, similarly, suppose if your body is connected with a cable or some link, then the direction of reaction will be in the line of cable or in the line of link. Okay, so you should always show reaction like this. And in the third case, suppose your body is on a collar, which is, and the collar is on this frictionless rod, so that this can move. Okay, so, and same is the case with frictionless pin in slot, so that this can move. So in that case, you will represent the friction reaction as perpendicular to this axis. Okay, so whatever this axis is, so you will take this 90-degree angle and you will represent the reaction like that. So in all these supports, the direction of the force is known to you. Now suppose we are having a frictionless pin or hinge. Okay, so your body is placed on a frictionless pin or hinge, or it is simply placed on a rough surface. Okay, so in that case the direction is unknown. Okay, so you have to represent the reaction force by F, for which you do not know the direction. Okay, so this alpha is unknown. Okay, and you can also break into the components. So suppose if this is your F, then this is will be Fx, and this will be F by Y. So in these type of supports, you have to show reaction force like this. While in case of fixed support, if your body is fixed at some location, then you have to add one couple also. So unknown force plus a couple. This is how you will show the reactions for fixed support. Okay. Now consider this body. So, and this body is in 2D. So we are considering the 2D case, equilibrium of a rigid body in 2 dimensions. Okay. So now for this case, because we are dealing with x and y directions, so Fz is 0, and similarly there is no moment in x and y directions. Okay, while all the moments will be in z directions. Okay, now what we can do, we can break all these forces into the components. So this P force can be breaked into Px and Py. Similarly for Q and S, then we will have the weight of the body, so that can be shown vertically downwards, and there are two supports. Okay, so at this support, this is a hinge type of support, so we will have an unknown and direction force, so which we can show by two components. Okay, and this is a roller type of support. So for roller type of support, we have just seen that the reaction force is perpendicular. So now we have placed all the forces. Okay, now there are three equations that will be formed with three unknowns. Okay, so these are summation of Fx is 0, summation of Fy is 0, and the summation of m at any point. So in this case we have considered a point, so summation of a is equals to 0. Now what we can do, we can always use some another equation also. So we can replace summation of Fy with summation of Mb. So always the three equations should be there. Okay. We cannot use four equations, but only three equations. But we can replace the equation. Okay. So we can replace fx also. In place of fx, we can use summation of Fy0, summation of Ma is equal to 0, and summation of Mb is equal to 0. So in this case, we can find the unknown forces. Some forces are known, some forces are unknown, especially reactions. So you can find the unknown reactions. Now, in some cases, some statically indeterminate reactions are formed. So there are three cases. So as you can see in the first case, in this case, more unknowns than equations. Okay. So you will be having four unknowns, but you can only form three equations. So we cannot solve this type of problem. Similarly, in this case, fewer unknowns than equations. So again, we are having fewer unknowns than equations. And this is partially constrained. Okay. So this figure is partially constrained, means in some direction its movement is not possible. Okay. So suppose you can see here we are having px, qx and sx, but there is no force in the negative x direction. Okay. So this is partially constraint. Here we are having no reaction force. Okay. No reaction force which can balance these forces. Okay. And similarly, we have again in the third figure also equal number equations and unknowns, but improperly constrained. Okay. So again, we do not have any reaction force in this direction. Okay. So these type of problems are not possible to solve. Now let us solve a problem related to equilibrium of rigid body. So this is the same figure which we have discussed, and we have also prepared the free body diagram. Okay. So this is our problem. A fixed crane has a mass of 1000 kg. So mass of this crane is 1000 kg, and it is used to lift a 2400 kg crate. So this crane is used to lift this weight, which is 2400. Okay. It is held in place by a pin at A. So here we are having a pin support, while at B we are having a rocker support. Okay. The center of gravity of the crane is located at G. So this is the center of gravity. Okay. And we have to determine the components of the reactions at A and B. And this should be the solution procedure. Create a free body diagram. Then determine B by solving the equation for the sum of the moments of all forces about A. Then determine reactions at A by solving the equations for the sum of all horizontal force and vertical forces. And then check the values obtained. Okay. So let us see the solution. So this free body diagram we have already made in the previous slides also. So we are using same free body diagram. So this is the weight, this is the weight of the crane, this is the weight which crane is lifting. So both will act downward, and at the pin support we will be having two reactions, while at the rocker support we will be having only one reaction. Okay. So now first step is to equate the moment at A equals to 0. Okay. So this is our A point. Okay. Now at A point we will be having the moment of this force and B. Okay. Now the moment of this B will be uh, uh, this is our A. Okay. So B will rotate in the anti-clockwise direction. B rotate in the anti-clockwise direction. So this is positive, and the moment of these forces are in clockwise directions. Okay. So they are negative. So B into 1.5. This is the 1.5 distance, and 9.81 into 2, while 23.5 into 6, this distance. Okay. So when you solve this equation, you will get B is equal to 107.1 kN. Now we will take summation of Fx is equal to 0. So in the x direction, we have only two forces, Ax and B. So Ax plus B should be 0. From this you can get A as minus 107.1 kilonewton. Now this minus sign means that Ax should act in this direction. Okay. Ax will act in this direction. And similarly, you can calculate by equating summation of Fy is equal to 0. Then in the y direction, we have Ay in the positive. Okay. If you are considering this as positive, then this is negative, this one. So three forces are there in the y direction. So sum of all the three forces is 0. Then you can get Ay is equal to 33.3 kilonewton. Okay. So this is how you can solve the problems of rigid body equilibrium. So thanks everyone. Thanks for watching the video. Have a nice day. Welcome dear students. In this video we will discuss equilibrium of a two-force body. So consider this body, and this is the T section, and suppose it is applied with two forces, F1 at A and F2 at B. Okay. Now for static equilibrium, the sum of moments about A must be 0, because we know that for equilibrium, the sum of moments about any point plus the forces resultant force should be 0. So the sum of moments about A must be 0, or we can do for B also. The sum of moments about B should also be 0. Now the moments of F2 must be 0. Now because F1 is acting at A, so its moment will be 0. Now for the moment of F2 about A to be equal to 0, it follows that F2 must pass through A. Because suppose if F2 is not passing through A, suppose like F2 is this, then there will be a component which will bring some moment. So for the moment of F2 to be equal to 0 about A, F2 must pass through A. Okay. Similarly, the line of action of F1 must pass through B. So similarly, we can do for this, for the sum of moments about B to be 0. Now considering these conditions, we can see that the sum of forces in any direction must be 0 leads to the conclusion that F1 and F2 must have equal magnitude but opposite sense. Okay. So if we want that two-force body should be in equilibrium, then the applied forces should be equal in magnitude but opposite in sense, and their line of action should also be the same. So this we can conclude. Now in this slide we have to draw the free body diagram for this problem. Draw the free body diagram of the dumpster D of the truck. which has a weight of 5,000 pound and a center of gravity at G. So this dumpster, it has a weight of 5,000 pound, and this is the center of gravity, and it is supported by a pin at A and a pin connected hydraulic diameter at BC. So there are two connections. This is the pin and this is pin connected hydraulic cylinder. Okay. So this is the free body diagram. So as we know, the weight, all weights acts vertically downward. So the weight force is shown here. Okay, and this angle will be 20°. Now this is the pin connection. So we will be having the reaction force with unknown direction. So we will be having two reactions, AX and AY, and at point B we will be having this type of reaction with known direction. So we have drawn the reaction force FBC. Okay, and this angle will be 20° plus 30°. So this is the free body diagram of this problem. So similarly we can draw free body diagram for any problem. Now let us solve one problem. This is a brake of the airplane. As an airplane's brake are applied, the nose wheel exerts two forces on the end of the landing gear. Okay, so when we are applying the brake, this will appear exerting the forces. One force is this and another force is this. Okay, on the landing gear. Determine the vertical and horizontal components of the reaction at the pin C. So here we have to determine the reaction and the force in strut AB, and we have to determine the force acting on this strut. Okay, so this is the free body diagram of this problem. So this is the reaction force. This is the applied force, 6 Newton and 2 Newton. So these are given in the problem. Now here we will be having two reaction forces at C. So we will be having this type of reaction force. So we can draw the two components Cy and Cx, and here we will be having one force in this direction. Okay, so we have drawn this FAB. Okay, and these are the distances, required distances. Okay, so they are taken from here. Now let us see the solution of this problem. So we have to equate the moment about C. So for equilibrium, moment of about C must be 0. So this is our C point. Okay, so we'll be having moment because of this force, and this force, three forces. Okay, so 2 into 1, this distance is 1. Okay, and the moment because of the two forces anti-clockwise, and 6, this is the clockwise. Okay, so we have minus 6 into, and this distance we can calculate by trigonometry, 110 20°, plus now this force will also have two components. Okay, so we have FAB sine 50° into 0.4 and minus FAB cos 50°, and this is the distance 0.4 tan 20°. So this must be 0. So when we solve this, we get FAB is equal to 0.864 kilonewton. Now we should also have summation of Fx is equal to 0 and summation of Fy should be equal also to 0. So in x direction we have this force. Okay, Cx, we have Cx, and we have this component, and we have 2 Newton. Three forces are there in the x direction, so we can write 0.8637 sine 50 plus 2. They are in the same direction, okay, minus Cx in the opposite direction. So when we solve this, we get Cx is equal to 2.66 kilonewton. Similarly, in the y direction also, we'll be having three forces, 6 kilonewton, then one component of this force, FAB cos 50, okay, and Cy. So from this we can get Cy is equal to 6.56 kilonewton. So this is how we can solve the problems of equilibrium of a two-force body. So this is all for this video. Thanks for watching. Have a nice day. Thanks. Welcome dear students. In this video I will discuss equilibrium of a three-force body. Now consider this body. Three forces are applied on the body, F1, F2 and F3. Now assume that the line of action of these forces F2 and F1, they are intersecting at point D. Okay. Now the moment of F1 and F2 about this point are 0 because these forces are passing through this point. So they will be having 0 moment because there is no vertical component. Okay. Now if the body is in equilibrium, so what it means? It means that the sum of the moments of F1, F2 and F3 about any axis must be 0. Okay. So if there is some moment, then it means that body is not in equilibrium. So if body is in equilibrium, then the moments of these three forces about any axis must be 0. So it follows that moment of F3 about D must be 0 as well, because the moment of these forces is 0 because they are intersecting at this point. So that means that the moment of F3 should also be 0, and the moment of F3 about D 0 means that F3 must pass through the same point D. Okay. So this means that the line of action of three forces must be concurrent. So this is the first condition of equilibrium of a three-force body, that the line of action of the three forces, that is F1, F2 and F3, must be concurrent. That is, they should pass through the same point or parallel. Okay. So that means that for equilibrium of a rigid body in 3D, 6 scalar equations are required, because summation of f should be 0 and summation of m should be 0. So we have three components for each. So that means that summation of fx, fy and fz should be equal to 0. Similarly, summation of mx, my and mz should be 0. That means that these equations can be solved for no more than 6 unknowns, because 6 equations, so we can solve them for 6 unknowns. Okay, we generally represent reactions at supports or connections. So the unknowns generally are reactions or connections at supports. Okay. We can also write in the vector form. So then we have only two equations: summation of f is equal to 0 and summation of moment about any point, which you can also write as r cross f, should be 0. Now, as we have seen the reactions at supports and connections for 2D, similarly in this slide the reactions at support and connections for a 3D structure are shown. So suppose if we are having this type of supports, ball type of support, or your body is placed on some frictionless surface, then there is only one reaction which is normal to the surface, this surface. Okay. Similarly, if we are having some cable, so then we have tension force, and the tension force will be in the line of the cable. Okay. Now suppose if you are having a roller type of support, or say wheel on rail, So in that case, there are two components. Okay. So that is, suppose this is in this direction moving. Suppose this is moving initially moving in this direction, then we will be having the reactions at Fy and Fz. Okay. And if the body is supported on some rough surface, or in case of ball and socket joint, we will be having three unknown reaction forces. So this is how you can draw reactions for 3D bodies. Similarly, suppose you are having some universal joint type of structure. So again, you will be having three unknown forces plus a moment. Okay. Now for fixed support, you will be having three unknown forces plus three moments. Okay. So you will be having six unknown for the fixed support. Sometimes you come across with these problems. Okay. So hinge and bearing supporting. So in that case, you will be having two forces. So we will um, we will not consider the axis of this. Okay, so we will be having Fy and Fz, similarly My and Mz. And now for this type of forces, pin and bracket joint and hinge and bearing supporting axial thrust and radial load, we will be having two moments My and Mz. Okay, because in the x direction this is moving. Okay, so we will not having mx, otherwise we will be having all the reactions fx, fy, fz and my and mz. So you should remember this whenever you are drawing the supports. So just remember this, and whenever you see, so suppose you got in your problem this type of support, then you can immediately draw these reactions. Now consider this problem. Problem is the uniform 7-meter steel shaft has a mass of 200 kg. As you can see, this is the steel shaft and is supported by a ball and socket joint at A. So here we are having a ball and socket joint. Okay, the ball and B rest against the smooth vertical walls. So other end is resting on these walls. Compute the forces exerted by the walls and the floor on the ends of the shaft. So this is the free body diagram. So at the ball and socket joint, as we have seen, there should be three unknown reactions. Okay, while at this there shall be two unknown reactions, Bx and By. Okay, so there shall be no reaction at Bz, as we have seen in the previous slides. Now this is the solution of this problem. So weight we can calculate m into g, and this distance. Okay, and this unknown distance h you can calculate by simply applying the formula. So we know this distance, we know these three distances. Okay, so this h height comes out to be 3 meters. Now this position vector rag, because this is our origin. Okay, this is our origin. Okay, so this is a and this is g. So rag will be minus 1 I. So in x direction this is 1. Similarly minus 3j plus 1.5 k. Similarly we can calculate RAB, which will be minus 2I minus 6j and plus 3k. Now suppose you want to calculate moment about A. So for equilibrium, summation of all the moments about A should be 0. So RAB cross Bx plus By means the moments of this because of Bx and By should be 0 plus this moment because of this force W should also be 0. So we have RAB cross Bx plus By plus RAG cross W should be 0. Okay, so this we have already calculated. Sorry, RAB and Bx and By they are unknown. Similarly, RAG, this we have calculated, and W we have calculated. Now you can write this in the form of determinant. So ijk minus 2 minus 6 3 and Bx By and B that is 0. Similarly, we can write for this. So our final equation will be this. Now equating the coefficients of I, J and K to be 0, we will get Bx as 654 Newton and By as 1962 Newton. Similarly, the summation of all the forces should also be 0. So we can have summation of Fx is equal to 0, summation of Fy is equal to 0, summation of Fz should be 0. So this is X, this is Y and this is Z. So by solving the equations, these three equations, we will get Ax as 654 Newton, Ay as 1962 Newton and Az as 1962 Newton. So finally we can calculate A as under root Ax square plus Ay square plus Az square. That means 654 square 1962 square plus 1962 square. So that will be 2850 Newton. So this completes the problem. So this is all for this video. Thanks for watching.